Hello students and welcome to the lecture. So students, as we know that we are covering the modern physics and so far we have done with the three parts. This is going to be the modern physics part 4. Okay. So basically in this lecture what we are going to talk about, we are going to talk about the thermal neutrons, nuclear reactor or atomic pile, fast breeder reactors, nuclear fission. In the previous lecture, basically we had talked about the nuclear energy, the nuclear reaction and the nuclear reactors and all. Basically in this lecture, we are going to stretch these topics further for the discussion. So if you have revised the previous lecture in the well enough manner, the thing will be easy for you to understand. And if you haven't revised the previous lectures, the thing might be difficult for you. In this, we will talk about the thermal neutrons, nuclear reactor, atomic coil, fast breeder reactors and nuclear fission. 4. Okay. But before starting the actual lecture, there is a small disclaimer, like always, that we are required to understand before we proceed further. Disclaimer is like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Let's begin with the thermal neutrons. So to obtain the thermal neutrons, in the chain reaction, it is sustained secondary fast neutrons are made to pass through the substance like the paraffin, deuterium or heavy water which are rich in hydrogen. On colliding against the hydrogen, the nuclei of protons of roughly equal mass, their velocities got interchanged with protons. The neutrons are thus got slowed down and therefore in thermal equilibrium with the material. These are what we call the thermal neutrons. The materials used for slowing down the fast neutrons are called the moderators. Examples are heavy water, graphite, deuterium and paraffin. So basically in order to obtain the thermal neutrons, what we generally do, that the sustained secondary fast neutrons actually forced by us to pass through substances like the paraffin, deuterium or the heavy water. Okay, these are actually rich in hydrogen. And the colliding against the hydrogen nuclei of protons, which having the roughly equal mass, velocities actually got interchanged with protons. And they got slowed down and therefore become the thermal equilibrium with the material. And now what we obtain is what we call the thermal neutrons. Okay, the material which we use to slow down these fast neutrons, actually the moderators, which are heavy water, graphite, deuterium and paraffin. Got it? Nuclear reactor or atomic pile. So a nuclear reactor is based upon controlled nuclear chain reaction. If you remember in the previous lecture we had seen that nuclear reaction could be both a boon or bane. If it is in a controllable manner, that could be used for various purposes for the betterment of mankind or humankind. But if it is uncontrollable, then it could have a disastrous effect on humankind and environment both. So that's why when we talk about the nuclear reactor or atomic pile, then here whatever reaction we do with the nuclear is actually the controlled nuclear chain reaction. It is a powerful device where in the nuclear energy produced is utilized for constructive purposes. Like we do the controllable nuclear chain reaction and whatsoever nuclear energy we got produced there, this energy is actually what we utilize for the constructive purposes. First nuclear reactor got established in the Chicago University under the supervision of Professor Fermi. Okay. There are several components of nuclear reactor which are as follows. First component is what we call as the nuclear fuel. It is actually a fissionable material to be used for the fission process to take place. Like nuclear fuel is the component that we are going to use in the nuclear reactor to produce the nuclear energy. Commonly used fuels in a nuclear reactors are uranium-233, uranium-235, and plutonium-239, etc. Generally, uranium oxide pellets are inserted end-to-end into the long hollow metal tubes constituting the fuel rods. When slow neutrons interact with the fuel, the fission starts and the energy got released. Now, the nuclear fuels are also of two types. First is fissionable material. So, on bombardment with slow neutrons, a chain reaction is directly produced, which leads to a release of tremendous amount of energy. Three fissible materials used at present frequently are uranium-235, plutonium-239, and uranium-233. Plutonium-239 and uranium-233 are obtained from the artificial transmutation. They are not naturally available. Then the fertile materials. Those materials which are non-fissile, we call them non-fissile in nature, but they could be converted into the fissile material by the reaction of neutrons. Then these are known as the fertile materials. For example, the isotopes of uranium-238 and thorium-232. These are the fertile materials and could be converted into the fissile material by the help of following reaction. 92U38 plus 0N1 equals to 92U239. It is like the beta decay equals to 93N59, and that again beta decay, then we could obtain this 94Pu239 or plutonium-239 we could call it. Then moderator. So moderator actually having a function to slow down the fast moving secondary neutrons that produce during the fission in order to control the chain reaction. The material of moderator should be light and should not absorb the neutrons so that the energy loss could be minimized and only the slowing down process for the fast moving secondary neutrons could be done. Usually, the heavy water, graphite, deuterium, and paraffin, etc., these could act as moderators. These moderators are actually rich in protons. When the fast-moving neutrons collide head-on with the protons of moderating substances, their energies got interchanged and thus the neutrons got slowed down. Such neutrons are what we call the thermal neutrons, which cause a fission of U35 in the fuel. Then control rods. They having the ability to capture the slow neutrons. To control the chain reaction from becoming violent, rods of boron or cadmium, what we call as a control rods, actually got inserted in the holes of reactor core up to a desirable length. As a result of it, the desired number of neutrons got absorbed and only limited number of neutrons left to produce the fission. These rods could be adjusted from outside the reactor in order to control the chain reaction. In addition to the control rods, the reactor also provided with safety rods, which when required could be inserted into the reaction or the reactor. They reduce the neutron reproduction factor K to less than unity. Then fourth is coolant, a substance which is used to remove the heat produced and transfer it from the core of the nuclear reactor to the surroundings is what we call the coolant. At ordinary temperatures, water and heavy water serve as coolant, but at high temperature, generally the liquid sodium is used as a coolant. The coolant takes up the heat energy produced in nuclear fission and passes on this energy to water in a heat exchanger. As a result of it, superheated steam is produced, which drives a turbine coupled with an electric generator. Then the shielding. Fifth, the whole reactor is protected with concrete walls of 2 to 2.5 meters thick so that radiations emitted during nuclear reactions may not produce harmful effects on the person that are working on the reactor. Working. Solar neutrons cause the fission of U-25 nuclei to start the nuclear reaction. The cadmium rods slowly removed, and to stop it, they are inserted. This brings out a controlled nuclear chain reaction, and hence the energy produced could be used for constructive purposes. Note, the nuclear reactors working in India are Apsara, Zarlina, CIR, Canada India Reactor, and Dhruva. Uses. Nuclear reactors used to produce radioactive isotopes, which in turn are used in medicine, the industries, and the agriculture. They are used in electric power generation. They could be used for the propulsion of ships, submarines, and aircraft. They are used to produce neutron beam of high intensity, which is used in the treatment of cancer and the nuclear research. Then what are the fast breeder reactors? Let's have a look on them. So they use the thorium or natural uranium as the fuel elements. When the fast neutrons strike uranium fuel in the reactor, U-38, which is present along with U-35 in the natural uranium, absorbs a neutron and becomes U-39. This is radioactive and undergoes beta decay twice to produce plutonium-239 as represented here. Like uranium-238 plus 0 and 1 equals to uranium-239, beta decay again, then N-239, beta decay again, and then you can say plutonium-239. Then again, it is uranium-235. Now, plutonium-239 is fissionable and undergoes the alpha decay with T equals to 24,000 years to produce the uranium-235. Thus, using an unfissionable material like uranium-238, we produce the fissionable material like plutonium-239, which could be fissioned even by the fast neutrons. Therefore, no moderator is used in such reactors. There is a note. In an atom bomb, nuclear chain reaction is uncontrolled, whereas in a nuclear reactor, nuclear chain reaction is controlled. Then, an unavoidable feature of reactor operation is the accumulation of radioactive waste, including both the fission product and heavy transonic elements such as plutonium and americium. Thus, the waste of nuclear power station is extremely hazardous to all forms of life on Earth. Elaborate safety measures needed not only for reactor operations, but also for handling and disposal of radioactive waste. Nuclear fission is actually the phenomenon of using two or more lighter nuclei to form a single heavy nucleus. Now we are talking about the nuclear fission. The mass of the product nucleus is slightly less than the sum of the masses of the lighter nuclei fusing together. The difference in masses, delta M, results in the release of tremendous amount of energy in accordance with two Einstein mass energy relations, where E equals to delta MC square. So we could say that the nuclear fusion is actually reversible of nuclear fission. In nuclear fission, we were breakdowning the heavy nucleus into the lighter nuclei, whereas in nuclear fission, we are combining the lighter nuclei into the heavy nucleus. So This is nuclear fission. This is nuclear fusion. It is just a reversible case. Some other examples of nuclear fission are H1 plus H1 equals to 1H2 plus E plus V plus 0.42 MeV. That is equation 1. Then 1H2 plus 1H2 equals to 1He3 plus N plus 3.27 MeV. This is equation 2. Third is 1H2 plus 1H2 equals to 1H3 plus 1H1 plus 4.03 MeV. This is equation 3. In all these reactions, we observed that the two positively charged particles combine to form a heavy nucleus. Column repulsion between these charges probates them to come close enough to be within the range of their attractive nuclear forces and got fused. The height of column barrier depends on the charges and the radii of two interacting nuclei. The essential condition for carrying out the nuclear is to raise the temperature of the material so that the particles have enough energy due to their thermal motions alone and they could penetrate the Coulomb barrier. The process is what we call thermonuclear fission. Thus, for the thermonuclear fission to occur, extreme condition of temperature and the pressure are required. Then further, higher density is also desirable so that the collision between the light nuclei occur quite frequently. These conditions are met only in the interiors of stars and couldn't be arranged in a laboratory. The energy generation in stars take place via thermonuclear fission. Stellar energy is the energy obtained continuously from the suns and the star. It is estimated that the sun has been radiating 3.8 into 10 power 26 joule of energy per second for billions of years. So, with this, we have finished this part also. It is requested and advisable to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.